Okay, so back to file systems. So today our goal is to finish the file systems layer and essentially be done with x86. Monday or not Tuesday is a midterm recap, right? Or not midterm, final at this point. And then Friday is next week Friday is a final exam, right? Same rules as usual, but we can go over on Tuesday as well. So okay, so last time we talked about the file systems, right? So we understand that they provide this human-friendly view of the disk. So if I ask you what file system is doing, what will you tell me? What are the main functions? Yeah, go ahead. Organization. So you essentially export just a bunch of blocks on the disk as human readable names, right? And so you can also provide a hierarchy. I mean, that's a design choice. You don't always need a hierarchy, and people argue whether it's useful or not. I find it useful for most cases. Sometimes I don't, but usually I like it. So for example, this is the reason why I recently moved from GitHub to GitLab, just because GitHub doesn't have projects, right? They say, okay, create a new organization. That's a hustle. So moving back and forth is a hustle as well. But you know, that's the value of the hierarchy. So what else? Say again? Right. So it provides a representation. So essentially, you say I have a continuous file which starts at 0 and goes to some max address. And of course, it's kind of like virtual to physical memory mapping, right? So the actual blocks on this can be anywhere, and the file system essentially keeps track. I was in a project in which we somehow, on a very tiny device, wanted to create files in a file system. I mean, we kind of failed, but the idea was kind of, you know, we only had like one layer of files, no directories. I don't know why. Maybe a total failure. It was actually on one of those digital rights management dongles, so essentially some files. But immediately you say, write a program. What's the convenient abstraction? You know, you have some storage. You can say, you know, I will just keep track of bytes or something, or blocks. But immediately, the moment you have 2 or 3 of these programs, you need to do what? You need to share the disk space between them. And so if you don't have this convenient naming abstraction and the layer which translates into where the blocks are, and this also, by the way, provides you a way to grow the file sizes dynamically, right? So each file starts with an empty inode, and we will see it today. But then as you write more into file, the file system will automatically allocate storage and disk for you, right? And finally, the last property which file system provides, which is very important, which people tend to forget. What is that? Persistence, right? But what is this like? Like, you know, there was a popular line of research just for the last 5-7 years. It's called persistent memory, right? So Intel came up with this product, Intel and a Micron, actually. Micron is here, and they have offices, I think, in Utah and in Idaho, if I remember correctly. And so they say, okay, we're going to give you DRAM, which is persistent. So it will keep data after reboot. Are you joining Micron or something? Okay, cool. In Idaho or here? Yeah, I had some friends who went there. But okay, so maybe you will tell me why. Why did they cancel it? So it was very popular to say, okay, we're going to build applications, and they will store their state like natively, like Microsoft Office or Open Office will open a file, just immediately put it in memory, and will never write it into the file system. So cutting the costs of going through the file system. But what do you think went wrong with this approach? Or what was like a biggest challenge, which essentially they were not able to solve really well?
If you have a program that's preserving static memory for itself, maybe that potentially cause issues with virtual memory as it gets backed up.
But imagine the way it was organized was the following. So you have like a special heap, and you can call it like, let's assume you have a special malloc, and you allocate objects on that heap, and those objects are persistent, meaning that if you somehow know the root, for example, of your object hierarchy, then you can discover the whole object hierarchy. So kind of similar to how from global variables you can maybe reach the parts of your heap. The real problem was the following. It was hard to ensure atomicity because imagine you update a pointer and halfway through updating the second pointer, machine crashes. And maybe not even, don't even lose power, maybe just the program crashes. And then often your entire heap, all the data which you accumulated over these months of running becomes garbage because you have this dangling pointer and you cannot really understand how to recover from this state. And so all these accesses need to be transactional, meaning you say, well, I need to update 5 pointers. And you do update them, but you need to have atomicity. So either all updates happen or none. And this is hard because, and actually it incurs the 2x overhead because typically you first copy the original pointers, start writing the new ones. And if you crash halfway, you restore the original ones. If you complete, then you throw away the original ones. But it's like twice, you access the memory twice essentially, right? So, and that was hard. So, and people came up with all sorts of frameworks, but they were still very, very complicated. So that wasn't fine. But I don't really know the reason why they canceled. I also have a line of research. I actually just got funding to do this. And suddenly they said, okay, Optane will no longer be there. So I don't know what to do now. But anyway, so it provides this atomicity. And today, like right now, this login layer is the layer which essentially does the same. So the login layer is effectively makes sure that if a file system, which typically anything like even a simple a simple write operation, which writes a block, you might say, okay, I'm just writing one block, so most likely it's just a single access to the file system, to the disk. It's not true because typically you say, well, maybe I don't have a block, so I have to go to the disk block allocator, figure out the new block which is available, mark the disk block allocator bitmap as taken. That's one write. Update the inode because you have to remember this new block is now belongs to a file, right? So that's write number 2 at least. And then actually write the data into the block, right? So that's write number 3. And maybe you have to update the metadata saying that, okay, by the way, the size of the file is now larger, right? So maybe like, and it can be combined with the write to the inode, right? So, but at least three different disk block accesses are required to do a single write in many cases, right? So then we have to ensure that if we suddenly crash halfway through doing those writes, right? Either those writes happen at once, all of them happen, or none of them happen, right? And I have a couple of examples here, but like I already like kind of explained what's going on. Okay, so if I ask you a question, and it's a nice design question. So again, imagine you have a file system. Imagine you have a disk. This is the disk space. Imagine you say, well, the virtue of my operation, which writes something to the file system, says, okay, I need to update this block number 1, block number 2, and block number 3. How will you solve this problem? How do you build a transaction? If you start writing one of them, wow, this write is happening, right? And then maybe you crash, then these two are not happening, and you're in inconsistent state, right? So you either have to make sure that all of them happen or not. So how to build such a system?
Did you like write them to like a temporary location and then move them when you're done?
Correct, exactly. This is how it's done. So you choose a temporary location, and which is called a journal or a log, right? Sorry. And you say, look, instead of writing directly here, I will write all of them here, block 1, block 2, block 3. And then somewhere here in the metadata area, I write something like, I have 3 pending writes, which means that at this point, you say, I know that if this write which writes 3 succeeds, I'm not going to lose those writes. If you crash writing 1 or 2 and then not updating this metadata, then you lost all of your writes. However, what you do next is say, okay, now I know that I remember I definitely have 3 of them here. You start copying them one by one into those locations, right? Into the actual locations on disk. If you crash, reboot, you see the 3 again, and you start copying from the beginning again, right? And until you reach the very last one, and you switch this 3 to 0 again, saying, okay, I did all the writes. At this point, I'm done, right? But this is the high-level overview of how you can build this transaction. So is it clear that if you crash any like at any point of time through those transaction, you will be able to either roll back to the state as if no writes happen, or you will be able to finish all the writes if you accumulated them here and updated the metadata area to reflect the fact that you have pending writes. If you're still writing block 2, if you're like just roll block 2 into the log, right? Here you still have 0, which means that if you reboot, you will lose all those writes. It's a general problem, right? It's kind of like it's exactly what I just, you essentially came up with a solution which I was trying to describe, but information might be lost. So for example, if you say, well, I remember we launched the rocket, and we about to make a record of it, but you crashed halfway, you didn't make this record, well, you will have to launch it again, I guess. So you cannot distinguish. So there are mechanisms for how you need to like build a transaction across nodes, build a distributed system in which, like, if only half of the system crashes or like minority of the system crashes, you know what really happened. But yeah, so it's called an output consistency problem. Okay, so if the high-level idea is clear, let's try to see how we can build it. Any other questions about the high-level idea behind the transactions, right? And essentially the same transactions were built for the persistent memory, right? But you can see how it becoming hard, but you will see in a second. So the way transaction goes is you say, well, we will start a transaction with the begin operation function in the kernel, and you will end a transaction with the end operation. And inside the transaction, you will be doing like block read. You will update the data of the blocks, right? So remember, block read fetches the data from disk, a block into the buffer cache in memory, right? So this copy is in memory. However, instead of doing block write here, you're doing a log write, meaning that you don't directly write this block back to disk. Instead, you use a log write function, which will write this log into some special journal area of the disk, right? So you will accumulate all the writes inside the transaction, and only will make sure that they will be committed to disk when you're done with all the writes, right? Okay, cool. So this is our data structure. So you have first you have obviously you have data structures which describe the journal or the log in memory and on disk. So in memory, what you have is that you have a log header which says, okay, you remember the blocks which you're accumulating as part of the transaction. You have this is the log header here. This is the log itself. You have a log which protects it, and you will see how the other fields are playing together to make sure that you remember which blocks you are actually writing. So let's first take a look at this begin op operation. So what it does is the following. So it says, I will try to acquire an entry in the log, right? And there might be multiple cases here because multiple processes are running on a system. Multiple processes are doing the reads and writes and doing transactions, right? So which means that you can have, you might be in a state in which you say, okay, someone else is committing the transaction, so let's go and sleep, essentially wait for it to be committed. There might be another case when you say, look, no one is committing, but the log itself, already multiple processes started enough transactions that the log doesn't have capacity to take another one, right? And essentially, in this case, you also say, okay, I'm going to sleep and wait until someone finishes, right? And you do the same pattern. So you pass the log into the sleep function, and when transaction commits, you essentially just, it will wake up. Will wake up all the waiters, right? And finally, the successful case is that you say, look, sure, I acquired the log here. I see that I have enough space in the transaction, in the log, right? So I will increment this counter, marking the fact that, okay, yet another process is trying to start a transaction. And transactions in x86 are limited lengths. So essentially, each transaction can have only max block size, right? And it's, again, a design choice, and you can build it differently, but this allows you to say, look, I have, for example, if I have 64 entries in the log, and I have 8 blocks per transaction, then at max I have 8 concurrent transactions at a time. It's not bad, like 8 concurrent transactions on a 2 CPU system is not bad. If you scale to 32 CPUs, maybe you have to reevaluate your design choices, right? And then you release the lock, right? Because you're allowing everyone else to add transaction to the log, right? So that's your begin op function, nothing else happening. Bread works as usual, right? So it's the same bread function. It just brings the block into the buffer cache. If it's already there, it just locks it, right? Saying, okay, I'm going to be reading it. However, the new function is the log write. This function replaces a combo of block write and block release, right? Which we used before. So what log write is doing is the following. First of all, so essentially you take a buffer as an argument. So what you're doing first is you check if this block is already in the log. Maybe you're writing the same block twice. It doesn't make sense to add it twice to the log, because it's okay to write it once, right? Because you just, in the end, the final state, the final data which you're writing to disk will be accumulated in the buffer cache, because the log, this in-memory log, just keep tracks essentially. Let me explain how it works. So if this is your log in memory, it has entries, right? And the entries are just numbers to the buffers in a buffer cache, right? So you just add a new entry saying, okay, my transaction has a block number 27. So when you start committing, you essentially try to get the block 27 from the buffer cache. You will first write it in the journaling area, and then you will write it from the journaling area to the position on disk, right? So, but here essentially, if you say, okay, someone tries to write this block twice, and I already have 27 in this log, instead of adding 27 again to the log, we just say, okay, I found it here, right? So, make sense? Okay. So, if, however, you don't find it, so essentially you search up until the log size, right? So you enter the new block number to the log, and you say, you mark the block in the disk buffer as dirty, because you say, okay, don't throw away this block because it's written, so we have to make sure that it's not evicted from the buffer cache. After that, you can release the log, right? So, okay, so far so good. So not super hard. You just remember, and that's kind of important. You just remember that this block is part of multiple writes in a single transaction, right? Agree? Okay, so and the way we track it is just essentially we have an array in memory for now. If you cross at any of these points, like you don't have any data on disk, right? Because you didn't write anything to disk yet. The whole state disappears, right? Okay, what happens when you try to end the transaction? Again, you acquire the lock, making sure that no one else is trying to concurrently change the log in memory. You decrement the number of outstanding transactions, right? However, you only start committing when you reach the counter 0, right? So typically, and you keep the track of it with this do commit flag. So essentially, if you really have to commit, right, So normally, if you didn't reach 0 here, right? You say, I will wake up everyone, whoever was waiting on the log, and I will just be happy with this. However, if you do commit, what you're doing here, you enter the commit function. The commit function is doing this 3 things which I was trying to explain you. So first of all, from the buffer cache, you will write all the blocks into the journal with this write log. After that, you will write the header marking the number of the log, number of the entries in the log, and in the journal area. So essentially, if this is your journal area on disk, so you will this write log function. If you have a bunch of buffers in a buffer cache in memory, like those are here, for example. So imagine this is a buffer cache. So what you're doing here is you have a log. This is your log in memory. It says, okay, look, I have entries in a buffer cache. You go through the log and essentially write them here, right? Write those entries here one by one. When you're reaching the end of it, you will write the header, updating with the number 3, for example. And after that, you will be doing an install transaction, which will be copying those to the actual locations on disk, right? And again, you reset the log size to n, to 0 here, marking that with this function write head, you will mark the fact that transaction is over. So let's take a look at how it works one by one. So write log, essentially just moving the disk blocks from the buffer cache to the journaling area. So what you do here is, again, you go through all the entry in the log, right? And you essentially what you're doing, you one by one, you read the block from the journaling area. So remember, the journaling area starts on disk with the beginning of the start block, right? And then you incrementing them one by one. So essentially, if you this is the layout. So essentially, you're going through the journaling area one by one, and you're skipping one because the first one will contain the header, this 3, which I keep mentioning, right? So that's why you skipped one. So you read the block, because in order to access the block, you have to always use the bread function. It brings the block in the buffer cache, right? Then you actually read the block, which is the block number, which your transaction is trying to commit. Remember that your log area contains only the numbers of the blocks. You say like, okay, I am trying to commit 77, 15, 7, and 33, for example, right? So you go through them, and those numbers are in the log. So you say like, okay, my tail is, for example, 2, this is 0, this is 1, this is 2. So you say, okay, I will get the block number 7 from the buffer cache, right? And you get a pointer to it. You acquire it for reading it with the bread function. At this point, you have 2 blocks, right? You can use just simply the move function to copy from data to the to data, right? And at this point, since you are writing this block into the journal, you correctly do the block write and release both blocks, saying, okay, I'm done. So at this point, they can be evicted from the buffer cache. The result of this operation is that this 2 block gets written in the journaling area, right? Is that clear?
So I want to clarify. The buffer cache you mean is on the memory or already in the disk?
So this function brings the block in the buffer cache.
The buffer cache is located in the memory or?
In memory. Buffer cache is in memory. You kind of have a guarantee that this from block is already in a buffer cache. Why is that? Don't only read from it. The reason it's part of the transaction is that it was written, right? So the log write function, remember, which replaces the bwrite. This function adds it to the log. If this is your log, when you do this log write function, internally, it will do the block read of this block. which brings the block in a buffer cache, right? And since you're doing the log write, you will do the block. You will mark, like, let's go back to the log write function. Just wanted to make sure that we understand it, right? So what I wanted to show you is that you actually mark the block as dirty, which means that it cannot be evicted from a buffer cache, right? So this block is already in a buffer cache. You're just getting a pointer to it. The to block, which is part of the journaling area, may or may not be in a buffer cache. So this to block, which you never touched before, maybe it's the first time you're touching it in recent time, might be on disk, and this will be brought into the buffer cache. If it's already there, you get a buffer cache hit, so you don't really have to go to disk, right? Okay, maybe let me finish with this, and I will do one kind of like picture which captures everything together. But let's just do this overview first, right? But okay, so this is what you did. So it's a loop. So you went through all blocks starting from 0 to log header n, right? And essentially just did this operation on them. So you say, I will bring the block into the buffer cache, and I will do a writing the blocks, not in their original location, but in the log area of the file system, right? So you did them, you wrote them here, right? That's what happened in this function. What you do next is that you say, I will write the header. Not surprisingly, this write the header just gets the block, which is the very beginning, the very start of the logging area, just acquires it for reading and writing. You say, okay, I will just typecast the log header. Like I will just typecast the buffer data to the log header, and I will just essentially write something into this log header. So I will write n, right? So if your transaction had n elements, you will write this n, right? And what you do here as well, you do need to remember the numbers, right? Like if you just write the n and you crash, you don't know the original locations on disk where the blocks have to be placed eventually, right? So what you do here is that you say, look, for each block number, I will remember the block number here as well, right? So you essentially create the same array on disk now, and you write it back on disk. At this point, if you crash after this write, your transaction will succeed. If you crash before this write, then all the writes will disappear after reboot. Is that clear? So okay, so you do this right. And at this point, you say, okay, so far so good. Time to essentially install the writes from the logging area to their original location on disk. Not surprisingly, it will be again a for loop, which essentially says, okay, I will be now going through my log in memory, reading the blocks, making sure that I have a pointer to the L stands for log blocks, log buffer, and this is D stands for data buffer. So this is from, and this will be to, right? Because you're writing from the logging area to the actual location on disk. So again, you say, okay, what's my block number? This might be a block number 77, as we said. You got them both with the bread function. You copy the data in memory, and at this point, you write the data block and release blocks, both data and log blocks, right? So essentially, you did the write into the actual disk area. At this point, you say, okay, time to commit. So essentially, you set the log header to 0, the number of transactions to 0, and you do the same write head function again, meaning that you're not going to do nothing much, but just simply update the block, the log header on disk, right? So let me go through the inodes and through directories, and then I will draw you a picture which essentially captures everything. So okay, so now we have atomicity. So essentially, you know how to combine multiple writes into a single atomic transaction, right? So at this point, you say, okay, we need to represent files somehow. So files don't have names, right? They just have numbers. The reason it works this way is that you have an area on disk which essentially has pre-allocated space in case of this file system, which says, okay, for this element number 0, it's a file, it's an inode, and it's the beginning of the file on disk, essentially. If you land on an inode 0, from there you will be able to essentially figure out all the data blocks of a file, right? Inodes, essentially, like everything in a file system, they have data structures on disk and they have data structures in memory, right? So essentially, when you start accessing the inode, when you open a file, you essentially say, okay, I will grab an inode in memory so I can keep track of what's going on, don't have to go to disk every time. But in order to get the metadata for this inode, I will read it from disk, from the same number, from the inode number on disk, right? So we talked a little bit about the inode, but in x86, the way the inodes represent files are with this data structure. So essentially, it has a little bit of a metadata. And the most important part here is the size and those direct blocks. So x86 says, okay, for the first 12 blocks, so blocks from 0 to 11, essentially, which if you have a file, so which consists of 5 12-byte blocks, right? So this is your inode or a file. They can be anywhere on disk, right? They can be essentially, it's kind of like, again, physical to virtual to physical memory mapping. So you say like, this is my block 0. In order to find which block it occupies on disk, you just make an entry here saying, okay, maybe block 15. So this is block 15, right? What about my block 1? So this is your block 1. Like you say, well, maybe it's in block on disk and in block 75. So you place 75 here, right? And you do that for the first 12. And then when you say, okay, the first 12, I already allocated first 12, what's next? Next, you say, well, I will allocate something what is called an indirect block. And again, you will remember that your indirect block sits somewhere on disk. So it sits maybe in block number 133. So this thing sits inside 133, and you remember 133 here, right? And here you will remember the next 128 blocks, essentially. Like that's your translation, right? And so every time you write, and I like, if you start with an empty file, all of these guys are originally empty, right? And you can do lseek, so essentially you don't have to write the files consecutively, right? So lseek essentially changes the position within a file. And I don't know how x86 handles it, so maybe it does allocate everything underneath, but a real file system will just skip those. And if you actually spilling, if the block number which you're trying to write lands on this area, it will just allocate this indirect block to contain the indirect mapping and essentially update something here, right? And then as you write more, you will start filling those entries in the direct inode and the indirect block, right? So it's kind of similar to how you build a page table, if you like, right? But on disk now. Okay, so inodes themselves, I said, okay, they look like numbers. So essentially, the file system reserves certain area on disk, which is split into these inodes, and this is the size of this area can restricts you to a specific number of inodes, the max number of inodes which you can have in your file system, right? So at some point, if you start creating a lot of files in x86, you will run out of inodes. Maybe you will run out of inodes faster than you run out of space in the data area, right? So, and essentially what you do is that you say, like, what is like I have inode number 5. So essentially you go to this array, fetch entry number 5, and read the metadata and create an inode data structure in memory to temporarily remember what's information and metadata about this inode, right? Okay. The actual representation of the inode on disk is relatively simple. So you have a file type, Why do we need file types? It can be either a file or a directory, because directories are contained inside the inodes themselves, right? You have a major and minor device number, and I forgot what it means, to be honest. This field, n links, number of links, remembers how many places in a file system refer to this inode, because a single inode can be, in a file system, can be remembered under multiple names. So essentially, you can create a file, say, okay, it's a file foo in a folder, I don't know, user bin. And this foo essentially, bin, which itself is a directory, will have a metadata table which says, okay, the name foo matches, like, is backed up by inode number 5, for example. Then you can link the same inode number 5 into another place in the file system. So something maybe under home Anton. And you can give it a different name. Maybe it will be foo bar, right? This directory Anton will remember that here this is bar, and it's still inode number 5. And every time you link, this n-link number is incremented by 1. So it will be 2 at this point. And the way to delete a file, so essentially it's kind of like a reference counting, because the file system itself doesn't know how many times you link the same file to different directories, gave it different names. So essentially every time you unlink, you decrement the counter. And when the counter drops to 0, then you essentially just, the file system deallocates the inode, making it free again. So, and remember, early in this class, I shown an example that if you want to create a temporary file, you simply open it and immediately unlink. And this way, essentially, it drops to 0. So the moment you close the file, the inode will be deleted. So it's a temporary file. So there will be it will not stay in the file system, right? Size itself, not surprisingly, represents the size of a file in bytes. And this is the area which says 12 first direct. I will remember numbers for the first 12 blocks plus 1 for one indirect block, right? And this this represents this data structure. So specifically this part in memory, right? So the max file size, obviously not surprising. So so 12, this first 12 by 512 plus this 128 by 512, so 71 kilobyte roughly. That's the max size in an x86 file system. And there are multiple designs for how to make sure that you can extend the max file size. You can, for example, use the last element of this indirect block to link to the next indirect block, right? And then you navigate this linked list to say, okay, I'm not landing on the first 127 elements, 127 blocks. Then I will search here, right, in the next element of this list. Or you can make this tree deeper. So essentially kind of this address just points to yet another set of indirect blocks, right? And then it's a radix tree, and again, you can represent larger files. And both of these choices were done in the past. So I think the linked list was used by FAT. I forgot what it stands for, but it's the file system which was used on Windows, and the hierarchical data structure is used in AXT 3 and 4 file systems. Okay, in memory, we represent an inode with a slightly different data structure. So essentially, it's similar, but it has the same type, major, minor, number of links, size, array of direct and indirect, but has those additional fields which track the lifetime of the inode in memory. So it has a number of the device which backs up the inode. So essentially, the disk number keeps the inode number itself, how many processes have opened the inode in memory. So every time you open a file, you create a new file data structure, but that file data structure will reference an inode, and you will increment this reference count, and then the flags busy and whether it's valid or not. Right, so this is to track whether the inode is allocated or not, because x86 will use an array of inodes for allocation. So x86 again doesn't use malloc to allocate inodes, but instead it uses this cache. So it says, okay, I have this array of n inode numbers, n inodes in memory, and this array is protected with a lock because you can open it from multiple processes, from multiple CPUs, right? So, and you call it an inode cache. So when you say, I want to open a file, the x86 will essentially search through this array, trying to find the one which is not busy, right? So a typical life cycle of an inode is the following. So you say, I want to open a file, allocate a new inode in memory, and the function ialloc allocates it from this array. Puts it back. Maybe it was allocated multiple times, so you just decrement the reference because maybe multiple processes open the same inode, right? And essentially you do this with this iget and iput functions. So the typical sequence of API invocation is the following. So you say, I want to open an inode number inum with an iget. You essentially says, okay, you lock it temporarily, saying that I want to do something, maybe like extend it, like adding additional blocks. Then you unlock it, and then you put it back, right? And essentially here in between, you can modify inode data structures. So here's an example of how iget might work. And works in x86 operating system. So essentially you say, for this specific device, I'm trying to open an inode number 77. So first of all, you say maybe it's already in a cache. So essentially you go through the cache, again, linear search, not the most efficient search algorithm in a file system. You say, okay, if I already have an inode, which is already like has reference count greater than 0, device matches, number matches, this is the inode which I actually looking for. So you increment the reference counter and return this inode pointer, right? So if, however, you say, okay, we didn't find anything, but you suddenly found if you're searching and you remember the very first one which was available, so the inode with the reference counter 0, you just remember that, okay, this one is the empty one and you can use it later. So you use it here, essentially saying, okay, that's my new inode, which was not in the cache. I will return this one. I will set the reference counter to 1 and return this inode pointer, right? So how do we read and write inodes? So remember we had this, okay, this is actually how it connects to the system call, right? So imagine we do a system call, which is sysread, right? What we first do, we fetch the arguments from the user, right? And then we do this file read. And file read essentially uses this file data structure, right? So if I ask you a question, where this F comes from? From user stack? Any other ideas? People who go to Micron, I'm sure they will ask you. Okay, who remembers the read signature, read system call? It takes how many arguments? 3. What's the first argument? FD. What is FD? Well, it's an integer, right? So it's a number, like 3, right? Then you have a buffer and you have a len, right? So here you suddenly have a data structure, F, right? So it's a real data structure. I'll show you what's inside. So how do the user passes a number 3. We suddenly get to the data structure F. How do we do this? Correct. So it comes from this file descriptor table. So if you have a process, proc data structure, internally it will have an array of file descriptors, right? It ties back to this very beginning of the class when we were talking about system interface. So user passes element number 3, right? So it just passes a number. If user already opened that file, there will be a pointer here. So 0, 1, and 2 will be standard input, output, and error, right? 3 will be a pointer to a file data structure, right? Agree? Okay, that's where it comes from. So this every time and this is part of your homework essentially. When you kill a process or when you kill a thread, you have to clean up this file descriptor, right? But when you create a thread, you create a new process data structure. That's one way to build it, right? I'm not arguing that you should do it this way, but it's one way to do it. And when you open the file descriptor, when you create a proc data structure, you copy the file descriptor table, right? So essentially, you will have proc of your parent process, which has file descriptor 0, 1, 2, and 3. And this 3 will also point to the same file data structure in memory, right? Okay, so file is not yet an inode. So why do we need multiple? So essentially, this is the operation. So you pass the file descriptor number, and this is the O file table, which has a pointer to the file, right? It may be 0, then you return -1 because the user might try to trick you into something, accessing something what you haven't yet opened, right? But that's essentially the layout. So you pass a 3 here, 3 goes into a table, file descriptor table inside the process, and this will have a pointer to the file data structure. So, which is right here inside the proc data structure. A file, okay. If I ask you a question, you can look at this actually. Why do you need this file data structure? What kind of semantics or what kind of meaning you try to encapsulate with this data structure? Because I said, inodes are kind of files, right? So they're files on disk. They don't have names. But yet I introduce yet another data structure, which is a file. So why am I doing this? Or why, it's not me, it's x86 writers or authors. So why do we do this? Why do we need a file? You can guess from looking at those fields. So essentially those fields encode the meaning of the data structure.
Maybe to count a number of references.
It does have a reference count, although let's take a look later how it works. That's true, but what else? Yeah, you keep track of whether the file which you opened you opened an inode, you opened it for reading or writing, so you keep track of it here with this readable and writable flags. What else? No, hold on. So one interesting thing that the file can be backed up by an actual inode on disk, or it can be backed up by a pipe, right? And we said, okay, you can read and write pipes and files through the same API, through the API of read and write, right? So this essentially like this encodes this polymorphism. So essentially you don't really, as a user, at some point you don't even know whether you're writing into a pipe or a file, right? You can figure it out. So if I say you're an attacker, so how can you figure out, are you writing into a file or into a pipe? Imagine you somehow got control of a user process by finding an exploit and try to figure out whether you're writing into a file under file descriptor 3. How would you do that? The operating system will not tell you, but how can you? So all the attackers are on YouTube online. They're busy finding exploits. Okay, again, students cannot answer, TAs will answer. So let's give students a chance.
Maybe by analyzing the evidence, we are writing.
But how? You don't really have an address. Right? So you read and write. Your write takes a number 3. And you have a buffer and a LAN.
Did you measure the time?
Yeah, I believe that first of all, you can measure the time, and writing into an inode will have a different time signature compared to writing into a pipe, especially if you write larger chunks. I'm also curious, however, about this other field, which is an offset. So remember, every time you write something into a file, you change the offset. And you also have an lseek system call to essentially say, okay, remember how we were doing loading the elf from the file. So we were seeking into a file to say, okay, I want to read from this specific location, right? So I'm not sure that you can do an seek on the pipe. So it's a good exercise, and maybe in some system you can, maybe in some system you cannot. But we can quickly check how x86 does it if it's a pipe, right? So maybe that also will give you this information. But reliably, you can also measure through a time. You can measure how much time it takes you to write something, and you can figure it out, right? But this seek is essentially one of the reasons why the file essentially is created every time, like for each process, because multiple processes can open the same inode, right? So this will be an inode. It represents the file on disk, right? So this data structures, but those guys will have their own private file data structures, which will essentially have different offsets here, right? So processes can write into different positions in the file, right? Okay, so okay, we got this. So, and also the pipe can be hiding behind the file. So when you do a file read, essentially you say, okay, if the readable flag is not set, you essentially return immediately. If the type is a pipe, you invoke the pipe read function. So ugly polymorphism at the level of C, but still kind of works, not bad. If the type is an inode, then you do the sequence of operations. You log the inode, you essentially use this read inode function, which says, okay, here's my inode pointer. This is the address of a buffer where I want to read something. And this is an offset and the number of bytes I want to read, right? And what you do here, you increment the offset. So essentially, you say, okay, I read some number of bytes, so I will increment the offset by this number of bytes, right? And this R is returned by the read-i function. So maybe you can read less than n because maybe the file is smaller, right? And then you unlock the inode, right? And you're done. So return to the user, right? So okay, this is how it connects to the system call layer. Read-i internally, what it does the following. So it actually read the inode. So this one takes the inode pointer. It has a guarantee that inode is locked, right? Because here we said, okay, ilock. So which means that probably it cannot be deallocated or destroyed from underneath you. You do a couple of interesting checks here. So obviously you check that the offset is not greater than the size, right? But if I ask you, why are you doing this check? What is this check?
Overflow.
What kind of overflow?
Integer.
Integer overflow. So what can go wrong? So really, if the offset is at the very end of the address space, so something like F, let's say 3 here, and your size is, I don't know, n is, let's say, F itself or 16, right? So then if you add this, so when you start reading, then at some point you overflow. And I mean, you can behave differently at this point, right? But I guess x86 tries to protect, so it says, okay, we don't want to deal with this condition when it overflows. And maybe it's a sound condition, because what does it really mean to overflow, to read from the overflow file? So it's better to return an error, right? So, and that's what they're doing here. But okay, so maybe like some more detailed analysis is useful. So next thing, so I mean, what you will be doing, essentially, you will be reading, right? So the user might pass n, which is relatively large, right? So maybe it's like even a megabyte, right? You can only read something from disk in the increments, in the units of 512, right? So hence, you will be essentially moving through the file, through these reads in the increments of either the block size or the like leftover read, right? So essentially you have to carefully read through this equation, but that's the idea here. However, for every offset within the file, right, you will be using this block Bmap function. So this Bmap function takes the offset within the file and it's divides by the block size. So essentially it takes the block number and returns you an actual block number on disk. So what do you think it does internally? So it essentially descends this, like it checks the first 12 direct blocks. If the block number is not among those, it goes into the indirect block, fetches this other block from disk, and essentially try to like figure out, like reads this entry and says, okay, really we have to read the block 77 from disk, right? So essentially, this is your kind of like walk page table function, which walks the inode and essentially resolves the offset within the file into the block number, right? And when you get it, so you say, I get the B read, I get the block number, you move the data from the block to the destination buffer, and you release the block, right? You're doing it in a loop because everything is in the unit of 512 bytes, right? So let's take a look at the Bmap function, which essentially just walks this data structure. So essentially, if I pass the number, for example, 7, it just lands right here and just reads the block number from here. If I pass something like 13, it says, okay, it's more than 12, so it has to read this block internally and read this entry, which is entry number. Logically, it's consecutive 13 from the block 13 from the beginning of the file. So, and this is what it does. So essentially, it says, okay, if a block number is less than the number of direct blocks, we'll just go into the array of inside the inode, like this is the block number. If it happens to be that this address is still 0, it means that this block was not allocated. So you happily just say, okay, please allocate me a new block. And essentially you go to the file system, allocate a new block, and return this new address which you got, the block number which you got, right? If you, however, is the block number is larger than 12, but still less than the max file size, you essentially do, okay, I will load the indirect block from disks. Essentially, you say, look, this is my inode. This indirect pointer, which is like number 13 here, right? Let's try loading it from, let's try first checking if it's not 0. If it's 0, then we'll allocate this one new guy on disk, right? And we will return this. If we'll set it up here. If, however, it's already allocated, so we'll read this block by doing this block read, right? Read the indirect block, and then you get the data. You typecast it to the array of integers because you have 128 integers inside the 512 bytes of a single block, and you essentially read the block number. And again, if it's 0, it was not allocated, you allocate. And by the way, you say it's a transaction, so this is actually since we're writing into this block, and it might be part of the transaction, instead of block write, you use the log write function, right? And at this point, you can release, right? Any questions about this function? It's essentially just translation from the block number within a file to the block number on disk. All good? Finally, block allocator, which we used here, like block alloc. Remember, we said, okay, it's a bitmap area, just uses 1 bit per block in a data area. So essentially meaning that if this one represents this one represents the second one. So relatively easy. The code which encodes allocation and deallocation is a little bit annoying. So it looks like this. So we're probably not going to spend a bunch of time doing it, but essentially just the logic is the same. You just manipulate the bits, trying to scan and figuring out the bit which you need, right? So just let's get to the directory layer. So the directory layer is the layer which essentially provides you human readable names. So essentially the way it works, at a high level, each directory is just a file which contains the following information. For each name, like foo, it will contain the inode number, 77, sorry. So you say, in this directory, foo is inode 77. If you suddenly happen that foo is another directory, then you read 77, it will also contain the same table, and it will have something like a bar here, inode 13, right? That's essentially the collection. So directories themselves are inodes on disk. Every time you create a directory, you just create a new inode. In x86, each name is a max of 14 characters, so this one is 14, and has a special inode type. Remember, inode had a type, so it's a directory type. So, and you have a couple of functions which essentially allow you to resolve human-readable names from directories. So directory is represented, as I said, this is just a table. So you say inode number is such and such, and this is a name, right? Okay, so how do we look up a directory? So essentially, again, linear search here. So what you do here is you check that this inode has to be a directory to begin with, right? Otherwise, we fail right away. Essentially, you linear search through all the entries of the array. What you do here is that you, from this inode, you read entry by entry. So you say, okay, look, this directory entry, which we just had on the previous page, is an inode number and 14 characters, right? So essentially, you read this entry from an inode. You have this read inode function. You do name CMP function, which compares the name which you pass here and the name of the directory. If it matches, you found it. If not, you essentially increment the position and move forward, right? So directory lookup is relatively easy. A more sophisticated lookup is the lookup from the pass name to an actual directory, right? So in order to do that, you first have to start, in order to perform this lookup, you start from the root directory, which is a directory itself, right? This inside the root, you will have a user entry, which will point to inode 27, for example. You go and read 27, and that this one represents the root, this one represents user. Inside the user, you will find a bin, right? It will have like inode 15, for example, and then you read the bin, and inside the bin, you will find sh, which will have inode 7, and this is actually, this inode will contain the sh file, executable, elf executable of the sh, right? So, but you need a function which essentially takes a pass as an argument and returns you this 7 or the inode, which you open when you pass inode number 7, right? So this function is called namei. We've seen it before. I mean, when we did exec, so remember we said, okay, namei, the pass which is passed from the user, namei returns an inode pointer, and then from there we were reading the elf file, right? So essentially, namei does this tricks. Essentially, just descends, uses a helping function namex, which essentially says, okay, if pass, which you pass here as an argument, starts with the root sign, with the slash, then we say, look, like user wants to start searching not from the current directory, because remember, each process has its own current directory. So when you start a process, you open that current directory, and when you close the process, you will close this current directory. So if this is not true, if the pass doesn't start from the slash, you essentially just get an inode of the current directory and then start searching from there. But if you do that, you say, look, I know the location of the root directory. It's when we create a file system, essentially kind of format the file system for the very first time, you essentially say, okay, this is my root device number, and this is my root inode number, right? And this is the inode which represents the root directory, right? So you first get this inode, right? Then you have a function which is called skip element. So essentially, if it has a, b, b / c, then it essentially splits it into b, b, and c and a separately, right? So you skip element, you get the pass, you get the you split it into name equals to A. So essentially you get A as the first, the prefix to the search string. You do a directory lookup. This is the prefix, this is the directory lookup of this A. You found the directory. If you're successful, you got the next. If not, you essentially exit, right? And so this is how you descend. So you go from one directory into another, right? And essentially at some point you reach the end, and essentially name I returns you an inode, right? Any questions, any quick questions about it? But essentially high-level story that directories themselves are inodes in the file system. They follow the same rules. You can use the same functions to read and write, but they have a well-defined data structure, so it's a well-defined layout. So you essentially know that it's each entry, it's an inode number and 14 characters for the name. And so you essentially can look up a name in a directory, right? But that's how it actually ties together. So when you do a sys open, right, you get an argument from the user at the pass. So you always do the name I, it returns you an inode pointer or not, right? And then and everything is done within a transaction, right? Because remember, okay, good question. So why do you need a transaction here? I don't know the answer myself. So can name I do it right accidentally? You need transactions if you do modifications to the file system. Why would you do this? Open opens a file. If you create a file, you do a create file. You do a create function. Okay, good question. So why not we assign it? And I was bad with assigning, but why not? I will try. So essentially, that will be the question for the weekend, which will help you to understand the file system a little bit more. And I will assign a couple of other questions. But just to make sure that, okay, yes. I mean, I don't know. At this point in time, I don't know the answer myself. I have to dig into the name I. Naively, it seems that the modification should not be happening when you open a file. Because okay, if it doesn't exist, you just return, and you don't write anything, so you don't allocate blocks underneath. But somehow, maybe it's some kind of a reference counter which they track to say, okay, look, if the file is open, right? So that's most likely the case. So you shouldn't really. No, I don't know really. Okay. So file descriptor layer real quick. So we already talked about it, right? So we talked about the file data structure, right? So essentially allows you to keep track of an offset behind the file descriptor. So every time you do a file open, essentially allocate a file from this cache of available files in the system, right? So you can run out of them as well. You say, okay, it's a type of inode, and you remember the inode here as well. File alloc itself, x86 maintain an array of n files, right, protected by a spin lock. So essentially you search in a table, and what you're trying to find is just simply an empty element, which has a reference counter 0. And then you essentially say, okay, reference counter 1. Why would you? This is the file descriptor alloc. Remember, searches through your table in a file descriptor table, trying to allocate the lowest available number. We talked about it when we were doing the operating system interfaces. So essentially, remember that open or duplicate will always pick the first available number. So essentially, it does search linearly starting from 0 to the end of the file descriptor table, and searches again for just a simply available entry which is 0. If it finds it, it puts F there, right? So that's how you essentially remember that you just allocated a file and you placed it in a file descriptor number, and you return the file descriptor number to the user, right? So thank you. Let me just quickly, so since we have like a second of time, let me just quickly just draw you a figure which captures everything together on one. So again, if you have a disk space, right? On top of the disk space, what you will have is the buffer cache. Buffer cache, remember in x86, it's just array of entries, which is maintained as a doubly linked list as well. So this one is a buffer cache. So when you do a block read and you pass a number like 77, it goes to 77. It first, like what it does internally, it searches if 77 might be somewhere over here, right? If it's there already, it just returns a pointer to this block, to this buffer. If it's not, it just reads into the buffer cache, right? So this is the block read, right? So, and if you just do a block write, it will just essentially flash it back into 77. If, however, you do this begin op and end op, you do a transaction, a journal, then you do a log write, right? And you say log write 77 again. What it does is that there is another data structure in memory, which is called a log. And essentially just said, okay, I will remember, maybe I had some already previous entries, and I will remember that I have to write 77, but no writes are happening. What you're doing, you just mark this as dirty, right? Agree with this? And it's, which means that this one cannot be evicted from the buffer cache because your deallocation policy will not touch the dirty blocks, right? When you end op, what you do is you say, look, I have a special area here, which is a log. The first is a header, and it has some number of entries. And essentially what you do here is you say, look, I will read this entry, let's say 7 here. And it will, let's assume it's sitting here in a buffer cache. So you have a block 7, you read 7, and you read, let's imagine this one was starting from log start. So this one is then log start plus 1. You read this one, read log start plus 1 to get it like it was the names which were given. This is to and this is from. And essentially at this point you say, look, I will, this buffer is read into the buffer cache. This one is start plus 1, and you essentially mem CPI, maybe it's block number, let's say this one is 20, this one is 21, so it's block 21, for example. And you mem CPI from here to here, right? From 77 to set, or sorry, from 7, okay, then you mem CPI from 7 into this 21, agree? And at this point, you do block write. You do block write of 21, essentially. This data gets written, right? Then you write all of them going through this log. Then you say, look, I have maybe 5 entries in my log. So you write 5 here along with the numbers. So this will contain the array, which has all the numbers like 7 and up to 77, right? And then you start copying those to essentially say, I'm going to commit. So you go through 7 and you copy from this one, from 21 to actually 7, which is logically somewhere over here on disk, right? And then eventually you go to 77 and you like write it here in 77. And then you update this entry from 5 to 0, right? Committing the transaction, right? So, but this is kind of the layout of data structure. So on top of that, you have an inode, and which essentially just keeps track of which blocks are where, kind of like a tree. And on top of that, you have a file, which keeps track of an offset within an inode. Right? So, okay, we don't have a homework for the file system. We will release an extra credit homework, which suggests you, which allows you to modify a file, which asks you to modify a file system. And then if you want to do some extra credit, so you will dig into the file system a little bit more. As I said, I will release a quiz, something about the file system, and hopefully it will clarify how it works for you, forcing you to do something on it. Okay, any questions at this point? Everyone wants to go. Okay, so then thank you. See you on Tuesday.
A few minutes back, you were talking about one of the slides related to begin transaction, right? Why we use begin transaction in open. So open parameters, it access two, right? One is path and another one is what is the mode, right? Whether it is a create function or whether it is a create or write or read, right?
Mix. I missed.
So basically, we have a open function, right? System call.
Yeah.
And that it accepts two parameters, right? One is a path name, file name, and second one is whether it is what kind of mode, whether it is a create mode or write mode.
Yeah.